Hi guys, so I'll be solving today's problem, which is Jump Game 4. I know it has been lately like I'm not uploading new videos because I have a lot of work to deal with. So yeah, so today I have less work, so I can give some time to make this LeetCode solution videos. Cool. So yeah, let's jump to the problem. So yeah, the problem name is Jump Game 4. Okay. Now the problem is asking that we have been given some integer arrays. Now we can make some jumps. Okay, and our final goal is to reach the last index. Okay, by starting from the first index. Okay. So if I say goal, okay, goal is to reach from 0 to n minus 1 index. Okay, and how to make it is via making jumps. Okay, now for any ith index I can jump to I plus 1, okay, or I can jump to I minus 1. Okay, so these are two types of my jump. Okay, now there is a third type of jump which says that if there exists a jth index, okay, such that array of I is equal to array of j, okay, I can jump there and provide that j is not equal to I. Okay, because I don't want to jump at the same place, right? I want to jump to a new place. So yeah, so three kinds of jump we can do. Okay, now our goal is to reach the last index starting from the first, but we have to minimize our number of jumps. Okay, so one trivial way of doing is like from the 0th index you just keep on jumping to the right. Okay, like 0 to 1, 1 to 2, 2 to 3, blah blah blah, to n minus 1. Okay, so with this you have a answer n. Okay, but we have to reduce this. Okay, cool. Actually this will be n minus 1, but yeah, cool. Now the thing is, now you have to observe some facts here. Okay, see, in your first case, like in your uh, like the first thing that can come to your mind is like, since jump game is a kind of series, kind of a problem. Okay, there is like jump game 1, 2, 3, and this is 4. Okay, and usually in that we solve that problem, solve this problem using dynamic programming. Okay, but here I think dynamic programming can be applied. Okay, for the time constraint I don't know how to apply it, but you guys can comment it if you can apply dynamic programming. But yeah, for this problem what I observed is, okay, so we have been given these kind of connections. Okay, and there is this word like minimum number of steps. Okay, now how can we minimize the number of steps? Okay, one way we can do it is via finding the shortest path, right, from 0 to n minus 1 index. Okay, so if I can find the shortest path, okay, by using the connections that I have been given. Okay, so if I write the key points here, okay, so we have been given connections. Okay, and the second thing we have been given is the minimum number of steps. Minimum number of steps. Okay, now this thing I can achieve if I can find the shortest path between 0 to n minus 1. Okay, so if I can find this, then I know like per step that's count as 1, so the length of the shortest path will become the minimum number of steps, right? So yeah, so with this I can think of like maybe DFS. Okay, or a better will be BFS. Okay, because all the shortest path algorithms, okay, are are kind of built via BFS only, right? So if you take Dijkstra, okay, so that is basically a BFS algorithm with a priority queue. Okay, so we can think in the direction of how to apply breadth first search here. Okay, now in order to apply BFS, okay, we need a graph here, right? Okay, but how to build this graph? Okay, so if we trivially think, okay, so if for every ith index, okay, if I consider this as my node, okay, so I can connect to this I minus 1 node. Okay, because from I we can jump to I minus 1. I can connect I plus 1 node to I. Okay, and I can connect all the j's, okay, such that array of I is equal to array of j, okay, to all this. Okay, let's say this is j1, this is j2, like this. Okay, but if I construct this kind of graph, okay, I'll hit a time complexity. Okay, because if I want to construct this kind of a graph, okay, what I have to do is I have to iterate over all the i's, okay, varying between 0 to n minus 1. Okay, so just think of this way. So let's say I create a hash map. Okay, now so I'll be doing g of I as a list. Okay, then, or maybe I will be pushing, let's say, I minus 1 and I plus 1 here. Okay, then again I have to start a jth loop, okay, again from 0 to n minus 1, okay, such that j is not equal to I. Okay, or I can write it something like this: j is not equal to I, and array of j is equal to array of I. Okay, so this is the trivial way of like creating this graph. Push back j. Okay, so if I do it via this, okay, I'll hit a n square time complexity, right? Because for every I have to like increment j again from 0 to n minus 1. Okay, so for every node I'll be doing n iterations, and there I have n number of nodes, so that will give me a n square time complexity. Okay, so we have to think something smart. Okay, so something crazy. Okay, so what we can do is, so for BFS traversal, okay, I'll be pushing i's. Okay, now this two thing I don't need, okay, because I know like for every I can look for the left guy, okay, I minus 1, and I can look for the I plus 1 guy. My main question is how to get this j. Okay, so I'll store only this j then. Okay, what I can do is I'll create my graph. Okay, and for every let's say I and le, okay, so for every value I'll just store the indices that contains that value. Okay, so let's say this is my range of this array. Okay, so what I will do is for g of le, I'll simply push back all the i's that contains it. Okay, now via this what I can achieve is, so when I'm inside the BFS and I'm at the ith node, okay, I can take the value of the ith node, okay, inside my graph, and I can directly jump to all those indices that contains the same value as my I. Okay, so with that, so when again some node comes, okay, let's say again some node comes, some, let's say, zth node, okay, that I'm getting from let's say q dot front. Okay, now for this guy, okay, I don't need, so let's say this z guy is coming via this ith node, okay, in my BFS. Okay, so for this guy I don't need to again traverse this graph. Okay, because this zth node, okay, will be associated with all of its j's values, okay, that I have already put in my queue via I. Okay, so maybe I will show you in the code, okay, how that is better. Okay, and yeah, that's the main idea here. Okay, we don't need to store this kind of a graph. Okay, we can store this kind of a graph. Okay, and we can utilize it, and it will be a hell lot of speed here. Okay, cool. So what I will do is I'll be coding in Rust. Okay, and I guess with that you will get a better intuition. Cool. So Rust is here. Okay, now let's first solve some trivial cases. So let's say I store the length of the array. Okay, then if n equal to 1, okay, if there is only one node, so I'm already at the last node, right? So I don't need to do anything, so I can simply return 0. Okay, now if n equal to 2, okay, so there is only one way to jump to the last node, okay, that is by jumping to the right. Okay, so in that way I'll be doing one jump. Okay, cool. Now when n equal to 3 comes, okay, so what I need to do is, so there are multiple ways. Okay, so let's say if I have been given something like this, 1 2 3, okay, this kind of array. Okay, so in this way, so I cannot directly jump here, right? So what I need to do is I have to jump here, I have to jump here. Okay, that will take me 2. Okay, but if I have been given 1 to 1 kind of array, okay, I can directly jump from here, right? Because these values are same. So in this case, only one step. Okay, now so for every array which has a length more than 3, I'll be solving for that. Okay, cool. So first thing first, I'll be creating a visited array. So I'll say visited. I'll create a vec of bull, and I'll say vec false n. Okay, now I'll be starting from the first index, which is the 0th index. Okay, so I can directly mark it here, visited of 0 equal to true. True. Okay, now in Rust I don't think there is any queue implementation, so I can directly use collections, like I can use a DQ here. Collections, I'll be needing hash map. Okay, and I'll be using DQ, data structure. Yeah, I guess this is the way. Cool. Oh, queue. Okay, visited done. Okay, now let's initialize first. Okay, so I'll be creating my graph, so I'll call it G. Okay, this will be a hash map which will be storing keys as i32, and it will be storing elements as a vec of i32, and I will be creating this hash map new. Okay, so this will be my graph. Okay, now I'll be creating my queue also. So my queue will be a DQ, so DQ. So I'll be storing a pair of integers, okay, i32 and i32, and I will call this guy vec DQ new. Okay, cool. Now I'll initialize my graph first. Okay, init graph. Okay, so I'll iterate over all the elements. So I'll simply say for I in range 0 to n. Okay, so I'll push the elements. Okay, so if my graph has an entry of array of I, okay, and if it doesn't have an entry, so I'll simply say or insert a new list. Okay, okay, and I will be pushing this element as i32. I32. Cool. So this will be usize, and since I have declared i32, so I'll be using i32. Okay, cool. Come to think of it, do I need anywhere? There may be a time when I'm at the 0th index and I'm doing a -1 operation. That time I'll face some issue, but yeah, okay, let it be, either do. Cool. Now the second thing is I'll be visited done. Okay, so first node I have already visited because I'm starting from that. Then I will push in the queue, so push back. I'll push 0 and 0. Okay, so what I'll be doing is, so inside the queue I'll be storing the node. Okay, and I'll be storing steps. Okay, so it's basically for this node how many steps we have taken from 0th index. Okay, and this guy will get minimized to for all the nodes. Okay, so yeah, and in the BFS inside the BFS while loop I will simply check if node is equal to n-1. Okay, so I can directly return steps. Okay, now why I can directly return steps? Okay, because BFS always gives me the shortest path. Okay, so I am starting from the 0th index. Okay, so if I have gotten a node which is n-1, that means I have already gotten the minimum number of jumps to reach that to reach the last index. Okay, so yeah, this will be the logic. Cool. Now I'll create the while loop. So let some node steps still there inside my queue, so I'll be popping pop front. Okay, cool. So I'll pop out the first element, then I'll first do the honorable thing, which is I will set node as usize, okay, because this is pretty essential, because this is Rust and it hates you when you use i32 as indexes. Cool. Now first thing first, I will check if usize minus is equal to n minus 1. If I have arrived at the like my goal or my destination, I can simply return steps here, okay, because that's the beauty of BFS. Okay, cool. So I'll be returning steps here, and here I can directly return some dummy output because my loop will always exit here, okay, but yeah, I need to return something i32, so let's return 0. Cool. Then what I can do is, okay, now if my node is not my destination, okay, so I'll check, I'll add the left part, okay, which is the node minus 1. Okay, so what I will do is, if u minus 1, no, here I have to do if node is greater than equal to 1, okay, and I have not visited u minus 1, okay, so here my node and u are basically same, but they are of different data type, okay. So for indexing in Rust, I have to use usize, so that's why I'm using u, okay. I cannot use node here because node is of i32, so these are some beautiful concepts in Rust, okay. That's why most of the people hate Rust. Cool. So I have this. Then what I will do is, if visited, if this guy is not visited, so I'll mark this as visited and I will push inside my queue the left guy, okay. Basically I'm jumping from I to I minus 1, okay. Cool. Then I'll push back this node, push back, I'll push node minus 1, and so till my node, if I have taken steps, like steps, number of steps, okay, so to go to the next this node minus 1, so I'll be incrementing by 1. Cool. Then similar thing, okay, when I'm doing I to I plus 1 transition, okay, so first thing I will check if here I can check like if u plus 1 is less than n, okay, if I am within the bounds, okay, then I can check if I have already visited this guy, okay. So if I'm within the bounds and if I have not visited my right guy, okay, so I can mark this guy as visited and I can push it inside the queue, okay. So I'll push node plus 1 and steps plus 1. Okay, cool. Now now the most useful part of our graph will come here, okay. See, so now I can use my node, okay, and all the entries, okay, in this graph that has the same value, okay. So what I will do is I'll simply say if let sum, okay, if there are any neighboring nodes, okay, for my current node, okay, nodes, okay, inside my graph, okay, and I'll be removing it, okay. So I don't need to use get, or maybe I will use get array of node or array of u, okay. So essentially what I'm saying is, okay, if I take this example here, okay, so my G is something like this, okay. So if I am drawing draw out my G, okay, and if I put here indices, this is, oh my god, what a stupid color, okay, 0 1 2, okay, I need to decrease its this thickness, and let's go 0 1 2 3 4 5 6 7, okay. So my G will look like something like this, okay. So for 7 I will be storing 0 7, okay, and for 6 I'll be storing 1 3 5, okay, and for 9 I'll be storing 2 4 and 6, okay. So this is how my graph looks, okay. So what I am now doing is I'm iterating over my, if you consider like if I am at the first index, okay, which is my node value here, okay, so I'll be iterating over this guy, okay, because I'm doing G of array of node, okay, and if my node is equal to 0, okay, then node value is 7, okay, 7. So I will be iterating over all the elements here, okay. Cool. So this whole thing is my n nodes here, okay. Cool. So for this, okay, so what I will be doing is while let some n node, okay, equal to n nodes dot pop. Okay, now here what I'm doing is, okay, so once I have reached this value now, okay, I will start from the last index, okay, and keep on collecting my n nodes here. Okay, so first my n node will become 7, okay, then in the second iteration of this while loop my n node will become 0. Okay, why I'm doing it? Because once I have reached this value, okay, and nowhere in the BFS iteration I'll be using this array of 7, because I want to get it finished as soon as I can. Okay, because that will help me to reach my n-1 node faster. Okay, because think of a scenario when you are again reiterating over this, okay, you don't need it, right? Because what will happen is for 0 you are traversing this, okay, and from this you will be pushing this 7th index, okay, inside your queue. Okay, 7, and let's say yeah, for 0, and you will be pushing 1 as a step, because from 0 you can reach to 7 directly within one step. Okay, now if you consider here, let's say there was one more element, let's say 8, okay, something like this, and our destination is 8. Okay, let's say 8 is also there, 8, and that's at the 8th index. Okay, okay, now let's say when I am at 0, okay, I pushed 7 into the queue. Okay, now think when 7 will become the front element of my queue, okay, I'll be reiterating over this guy, okay, because my array of 7 will give me this 7 value, okay, and I will again reiterate over 0, again reiterate over the 7. Okay, I don't need that, right? As soon as I get a node, I will flushing out all the elements in its value array. Okay, value array, I'm saying like the graph of value, whatever this n nodes array I'm getting. Okay, so that I don't need to reiterate over it. Okay, otherwise I need to I will have to maintain some kind of value visited kind of array, okay, which will mark that, okay, I have already visited this value, I don't need to mark it, like I don't need to visit it again, or something like that. Okay, so in order to avoid it, I will simply pop back elements from the back of this list, okay, and I will be pushing inside the queue. Okay, so this is what is happening. Okay, cool. Now I got some n node n like neighboring nodes. Okay, now I'm iterating over all the neighboring nodes by popping out the last element from my neighboring nodes. Okay, now I'll check if I have not visited this node. Yes, what I can do is, okay, I have to use usize. Okay, so if I have not visited this n node yet, okay, so I'll mark this n node as usize as visited. Okay, and I'll push this element with n node as my element and steps +1, because from node I can directly jump to this n node. Okay, because both of them had the same value. Okay, now the thing is, since I don't need to reiterate it, okay, so with this the length of this guy will become 0, but I guess I don't need to keep this key also. Okay, so what I can do is I can directly remove this guy. Okay, so once I'm done with this, I'll simply flush out this guy, so then only 6, 8, 9 will be remaining. Okay, cool. And yeah, so in Rust, when you remove a field from a dictionary, it gives you it returns you the value, so I'll get this value. Okay, and I need to do mutable because I'm popping out, right? So it shouldn't be immutable. Cool. So with this, I'm hoping I'm done. I'm not sure, but let's run it. Compilation issue. Okay, so I got a compilation issue because there's a block, not an array. Oh, okay, sorry, I used curly braces. I'm so fond of C++. Cool. Oh shit. Oh, collections. Bada boom, bada boom. Bing. Cool, it passed. Now let's submit, and voila, it got accepted. Okay, now let's look at the time complexity here. Okay, so let's look at time complexity. Okay, now here, all these are like constant step. Okay, this is kind of a linear. Okay, but we don't include that in time complexity, but okay, let's include that. Okay, so that is visited array creation with all the false values for n, so that is big O of n. Okay, then we have this init g. Okay, now if you observe this init g, to initialize g we are iterating over all the elements and we are touching every element once. Okay, so this guy is big O of n again. Okay, now let's go to our BFS loop. Okay, so inside this BFS loop I'm getting this node. Okay, then I'm pushing all the nodes inside my queue again, like whichever, say from my from my current node, whatever nodes I can visit, I can jump from this node, I'm pushing those nodes inside my queue. Okay, so and and yeah, because of this visited array, okay, I'm not what revisiting those nodes again. Okay, so I can say I'm touching every node once inside my BFS loop. Okay, and yeah, so that's again a big O of n. Okay, cool. And there is this removal operation. Now this removal operation is constant in Rust. Okay, because we are simply removing this pointer from the graph. Okay, there is no like for loop iteration over every value removal. Okay, it's just a key value pair, it just removes the whole thing. Okay, so this guy is constant. Okay, now this part, okay, while nodes dot pop. Okay, so since I'm completely flushing out all the elements inside my value array. Okay, so I will not get that value array in any other future iterations. Okay, that means my BFS loop guarantees that I'm touching every element once. Okay, so if I'm touching every element once, so my complexity will become the number of elements, big O of number of element, which is big O of n. So I can say I have an overall time complexity of big O of n. Okay, now about the space complexity. Okay, so I'm creating visited, which is storing n. So as my n increases, this will also increase linearly, so there is a big O of n here. I have hash map. Okay, now inside my hash map, okay, I'm storing the values as the keys and all the indices as the list of indices that contains that value. Okay, and that is basically you can say it is supposed to be like big of n. Okay, okay, so if you assume like the worst case, okay, so we have all unique n elements. Okay, so I'll be storing the value, okay, and the corresponding index. Okay, so that's kind of 2n space here. Okay, 2n space at max we can get. Okay, but yeah, we basically store the values in key value space in pair, so that is mostly like n entries we'll be doing here, so it's linear again with n. Okay, cool. Then we have dq, and dq at one point of time will be storing all the nodes. Okay, and that's the worst time complexity, and with this yeah, so it will be again big O of n, big O of number of nodes. So yeah, it's again big O of n. Cool. So these are my time and space complexity, so it is pretty efficient. Cool. So this is with Rust. Okay, we are the middle. Okay, so which is good. Okay, now I'll be showing you the same code in Golang. Okay, so in Golang we also do not have any inbuilt queue data structure. Okay, there is a list data structure which we can use. It act as a linked list. Okay, it's basically a DQ. Okay, so yeah, so in Golang what I have done is, again I'm storing the length of the elements. I have created visited. I'm using the DQ as my queue here. Okay, now just for a little bit of structuring, I have created a struct here which will store the value. Okay, value of the node and the steps and the steps is basically the same, like how many number of steps I have how many minimum number of steps I have taken from my 0th index to reach this value. Okay, so this value basically stores index of the element. Okay, cool. So again the same thing, so I'm creating this graph. So graph is storing values as keys and appending all the indices that contain the same value, and this is my BFS loop. Okay, until my queue has some length. Okay, um, so here what I have done is, so I have this nodes. Okay, now this nodes is basically I have created the length of the queue. Okay, so basically I don't need this. Okay, I can directly use this part. Okay, so yeah, I'm popping out the front element from the queue and removing that element, and I'm doing a typecasting here. Okay, because what happens in this list of container is this guy is kind of a pointer here. Okay, now in order to get the value here, okay, a value of this pointer, I have to use this dot value, which is basically dereferencing that pointer, and then I have to typecast it. Okay, then I'm typecasting it to this node structure. Okay, so with this, for this pointer I will get the corresponding index and the steps. Okay, then the code is pretty similar. Okay, I'm checking my bounds. Okay, whether I can jump to the left index I-1. Okay, and whether I have visited it. If I have not, mark it visited, push it in the queue. Similarly for the right part, which is I to I+1 transition. Okay, check whether I can move there. If yes, check whether I have visited it. If I have not visited it, mark it visited and push it to the queue. And similarly here. Okay, so I can zoom it a bit. Okay, oopsie, lots of zoom. Okay, similarly here, so I'm storing all the neighboring nodes that I have for my current nodes value. Okay, for all the nodes. Then yeah, I'm just popping out the last element. Okay, which you can see num and nodes -1. Okay, popping out the last element and squeezing my value array here. Okay, by truncating by n-1, you can say. Here n is basically the number of nodes I have in my neighboring nodes. Okay, then yeah, I am checking whether my current neighbor node has not been visited. If it has not been visited, mark it visited and push it in the queue with the steps +1. Okay, so the ideology is same. Okay, just the syntactic difference. But yeah, if I run this, I hope it will work. And voila, it worked. If I submit, and I'm at the end, which is fine. Okay, cool. And now for the last part, this is my C++. So this thing, so this is where I solve the problem first. Okay, I'm just like thinking in my mind whether BFS is the solution. So yeah, so same syntax. Okay, so I'm creating my map data structure for my graph. Okay, and I'm storing for every value the indexes that contains it. Okay, then I have my queue data structure, which is storing a pair of integer, basically the node and the steps that I required to get to that node, starting from 0th index. Okay, then I have this visited, marking my visited as true. Then I have my BFS loop. Okay, where I'm unpacking node and steps. Okay, then I'm checking whether I can pop out from I to like node to node -1, which is here. But yeah, here I'm checking whether I have already reached the destination. Okay, so here I was doing answer greater than steps, so I can remove this. I can directly return steps here. Okay, and I can remove this break statement, and this answer I can remove this, and I can return 0 here. Okay, cool. So this thing are same. So whether I can go to node -1, and similarly here node to node +1, if I can go there. So I'm marking them visited and pushing into the queue. Okay, then yeah, nodes having the same values. Okay, I'm collecting the size. So inside the while loop, I'm basically iterating over all my neighboring nodes. Okay, then yeah, one by one I'm just popping them back. Okay, collecting my current neighbor node and checking whether I have already visited it. If I have not, then push it in the queue and mark it visited. So yeah, with that, the BFS will guarantee that it will always give you the shortest path between your starting index to the last index. And yeah, cool. So again at the middle. So but yeah, the good thing is it got accepted. Cool. So I hope you learned something new. Okay, and if you see, like, the problem was not that difficult. Okay, it's basically the challenge was basically how do you construct the graph for your BFS. Okay, and how do you apply it in the BFS. So that was a major challenge, and I don't think it's a pretty hard problem. It was a pretty easy problem. Cool. So if you like this video, please do like, subscribe to the channel, and you can share your like, you can put some comments if you have any doubts, and anything you didn't understand in the video, so you can put it there. So yeah, cool. Bye bye.